Hello, everybody, and welcome to today's lecture on data preparation. We will focus on advanced techniques beyond what we've covered in part 1. I am Dr. Andrei Holtz, and today we'll cover feature engineering, feature selection, dimensionality reduction, and much more. Those approaches will help us make our machine learning models not only accurate, but also reliable and robust. Let us get started, and let us begin with a short recap of the core steps in data preparation. So, data collection is our starting point. It's all about sourcing our data from different places. Then we move to data cleaning, where we handle missing values, duplicates, outliers, and all around it. This is a crucial step that ensures the quality of our data. Next is transformation and encoding. And here we normalize numerical features and encode categorical ones, making the data digestible for machine learning algorithms. Following this, we deal with feature selection and generation, identifying the features that matter most and creating new informative features. We also perform dimensionality reduction, reducing the number of features while retaining essential information. And another crucial step is splitting the data for training, validation, and testing, implementing cross-validation to ensure our model's reliability and, of course, to prevent data leakage. And finally, we automate all the steps using data pipelines and making our process repeatable and efficient. Today, we will focus on advanced data preparation. We'll discuss feature selection, which helps us determine the most relevant features. Feature generation, where we create new insights from existing data, and dimensionality reduction, which helps mitigate the curse of dimensionality. We will also discuss the importance of proper data splitting and cross-validation. I'll show you why avoiding data leakage is so crucial, and we'll wrap up by automating all these steps into a robust pipeline. And just to remind you, the CRISP-DM, or the Cross-Industry Standard Processes for Data Mining, remains the cornerstone for data analytics. This iterative process starts with understanding a business problem, moves through data understanding, preparation, modeling, evaluation, and deployment. And today, we are talking about the preparation phase. This phase takes a bulk of the effort of the entire project, and it is crucial in building effective models. The more solid our data foundation is, the better our the more solid our data foundation is, the better our models perform. Just to highlight the preparation stage, this step involves multiple iterations and requires a thorough understanding of your data to effectively prepare it for modeling. The data preparation phase includes cleaning, transformation, feature engineering, and ultimately making sure the data is in form suitable for our model. Now, why advanced data preparation? Well, clean data is the bare minimum. Beyond that, it's all about engineering the right features, reducing dimensionality, and transforming raw data into something our models can truly benefit from. Today, I would like to emphasize that good feature design is often more important than the choice of the model's architecture. Even with the most advanced algorithms, garbage in means garbage out. So we need to get this right. Before we dive deeper, let's briefly touch on two foundational models. The linear regression is our bread and butter. It finds a line that best predicts a continuous outcome. Simple, interpretable, and powerful when relationships are linear. And then we have decision trees, which are great at handling both regression and classification tasks by splitting the dataset into branches. Decision trees are the intuitive and easy to explain, but without careful tuning, they can easily overfit. We will cover the details of each model during another lecture. Today we will need them just to illustrate some techniques of data preparation and pipelines. Clean data is necessary but not sufficient. We need meaningful features, and the quality of our data splits is critical. And imagine working with 100 features. Some may be irrelevant, others may cause more harm than good by adding noise. Our goal here is to remove redundancy and optimize features, prevent the models from overfitting, and help them learn generalizable patterns. This brings us to feature selection. And feature selection is about removing what is unnecessary. Including irrelevant features is like adding too much seasoning to a dish. It masks the true flavor. Redundant features not only complicate models, but also increase the risk of overfitting. And today we'll explore methods to reduce dimensionality while maintaining predictive power. Let's look at three main types of feature selection methods. First one, filter methods. These methods evaluate the importance of features based on their own characteristics, like correlation or statistical tests. Examples include correlation matrices and chi-square test and weight of evidence. Next, we have wrapper methods, and these methods select the features by testing different combinations and evaluating how well the model performs, such as using recursive feature elimination. And finally, embedded methods. And these methods select features during the model training process itself. For example, lasso and ridge regressions add penalties that reduce the influence of less important features. Each of the methods has its own strengths, and choosing the right one depends on your data and your goals. We start with filter methods. Correlation matrix, chi-square test, weight of evidence. Filter methods are fast, simple, and model agnostic. Let's move to the first example. Predicting house prices. And if the number of bedrooms and number of bathrooms are highly correlated, keeping both might not add as much value to the model, and we'll need to choose the one that we remove from the dataset. And correlation matrix is basically a matrix. It measures like linear relationship between numerical features. It utilizes correlation coefficients, and coefficients varies from -1 to 1. T-square test comes from statistics. It tests hypothesis that feature is significantly related to target. And it is particularly useful when dealing with categorical features, evaluating how well observed frequencies match expected ones if features and targets were independent. For instance, here we need to check whether the region significantly related with the target and targeted like this was there like the sale from this region, and we need to know the effect, and we can do so by calculating the observed and expected frequencies and then checking the chi-square statistics and checking the p-value. And for this particular example, there is not enough evidence to conclude that the feature is significantly related to the target at the 5% significance level, since our p-value is above this. And this our p-value is calculated for the chi-square statistics and degrees of freedom. Weight of evidence, commonly used in credit scoring, helps encode categorical variables, making them informative for our predictive models. For instance, in banking, education level can have significant impact on predicting loan defaults, and weight of evidence helps quantify that impact. You can take a look at the formula and it's not rocket science. Basically, you need to calculate the percentage of zeros and ones for a specific bin, and then then you can calculate it. And after this, you can calculate the information value that will show you how important the feature is. And we are moving to wrapper methods. So those methods tend to provide higher accuracy as they directly interact with the model, selecting features based on performance metrics. But this comes at a computational cost. Methods like forward selection and backward elimination add or remove features one by one, while recursive feature elimination, or RFE, and exhaustive feature search explore various feature subsets to find the most optimal. Although they are powerful, the methods can lead to overfitting and require careful validation. And moving on to embedded methods. And we start with decision trees and feature importance. A decision tree is like a game of 20 questions where we ask the best questions to help us figure out the answer. The most important questions are the ones that help us make the best decisions. And decision trees rank features by their ability to split the data effectively. This means separating our observations in ways that best predict the outcome. As the tree is trained, each split provides a measure of how much that particular feature reduces impurity. And we can measure impurity by different metrics. We can use entropy, or we can use any other function. The features that lead to a significant reduction in impurity are considered to be more important. Let's have an example. If we want to know if someone is good at paying back a loan, the decision tree might ask questions like, how long have they had credit? Or do they have a lot of unpaid bills? The tree figures out which questions are the most helpful and ranks them. The graph shows that some questions are more important than the others, like feature 2, the most important one, huge importance. I would say you should be cautious when you have this much importance of the feature. That usually that usually indicates that there might be something wrong with the data or with the model. This helps us know which things really matter when making decisions. Embedded, embedded methods like lasso and ridge are favored in industry for balancing feature selection and regularization. Basically, those methods are linear regression regularization techniques. L1 or lasso works well when we believe that only a few features are genuinely predictive. It shrinks the rest to zero since it utilizes the abs, not the square, the absolute value. Ridge or L2, on the other hand, reduces all coefficients but does not eliminate them entirely since there is a square here, but doesn't eliminate them entirely. This this is useful when we think many features contribute, but their contribution varies. This is the table where you can see the pros and cons and the recommendations for each method, where to use it. So take a look at it, and I hope that it will be helpful during the practical session. Let's take a look at how those feature selection methods work in place. I'll be showing you how to implement both filter and wrapper methods in Python and we'll see how different subsets of features impact model performance. Welcome to the feature selection demo. Today we'll discuss filtering methods, wrapping methods, and embedded methods. Filter methods are statistical techniques to assess the relationship between input features and the target variable, selecting those with the strongest associations. And as an example of those methods, it's a correlation matrix with different correlation coefficients, chi-square test, weight of evidence, ANOVA, and mutual information. So the wrapping methods, it's forward and backward selection, recursive feature elimination, and exhaustive feature search. As for the embedded methods, so those are methods that perform feature selection during the process of model training, using the properties of specific algorithms. Let us start import all the necessary libs. The dataset we're using is Census Bureau database. It contains several features like age, work class, education, marital status, race, sex, and so on. The target here is to predict whether a person makes over 50K a year. Well, it's a bit outdated. Data is from 1994. We're interested here in taking a look at the dataset just to know its shape, the length of the dataset, and the number of features. So we have 15 features, including target feature. Target feature is class. That's classification dataset. As we can see here, there are several nulls, especially for work class and occupation in native country. Let us have the description of the dataset just to take a look to know that age is between 17 and 90. Interesting. The most popular marital status is married civ spouse. As for the most common indication is a high school graduate. Again, we need to know which features are which, since some algorithms work only with a specific type of data, so we'll distinguish categorical columns and numerical columns, and we'll just fill categorical columns that are NA with label no data. So as of now, we do not have any missing values, and we're okay to start. Let us specifically create several highly correlated features just for educational purposes. We'll create a feature correlated with education number. We'll create highly correlated with age, correlated with target, correlated as a categorical feature with the work class, and we'll create a nonlinear relationship between education num and the new feature. So those are our new columns. Let us add our new columns to the numerical and categorical ones. Now we're ready. We start with filter methods. And the first and the most common one is correlation coefficients or correlation matrix. Basically, correlation matrix shows the relationship between numerical features. By default, we use Pearson correlation, which assumes a linear relationship between features. And let us calculate it. Take a note at the time required to calculate the whole thing. It's a Pearson correlation matrix for numerical features. We can notice here that age marked as 1, so it's highly correlated. Education number, again, highly correlated, and target is not that correlated, which is strange, but let it be so. We can notice here that nonlinear relation is also captured, but not as like strong one, but still it's a notable correlation. What if we try the Spearman correlation? It measures monotonic relationships, both like linear and nonlinear. As you can see, it takes more time to process. And here again, we see this similar picture. The fake or the synthetic features show higher correlation, which is good. And let's take a look at the candle correlation. Yep, similar picture. However, if we take a look at education num nonlinear and education num correlated, they are not that much correlated as they should according to Kendall. A relationship between numerical and binary target or just binary feature. We can do so. There is a binary point biserial correlation. And let's take a look at it. What it shows us basically is that correlation between high correlated target and target is super high. That is true since we introduced this feature as a fake feature. Apart from that, the other features, apart from that, the other feature seems okay. And it should be treated similarly with the positive and negative correlation. What else here interesting is that it provides p-value, and like the smaller p-value, the more significant this correlation is, and p-value is 0 for our case. What if we need to measure two categorical features, like the relationship between two categorical features? We can do so. There is like Kramer's V approach. It basically uses chi-square, but let's take a look. It's pretty interesting. A lot of features here. Let's. We can notice here that there is a correlation between work class and occupation, which makes sense. What else? Yeah, one. Work class and work class highly dependent. Well, that is expected. Marital status and gender. Well, why not? Type of correlation there. But since it's 1994, so maybe occupation and sex, not gender, relationship and sex, race and native country. That is interesting, since it's like obvious, but this mathematical, statistical, but the statistical method shows this. And we're moving to the mutual information. Mutual information quantifies the amount of information gained about the target from knowing the feature values. It works well for both numerical and categorical features, and it is useful for nonlinear relationship. So it is not bounded between 1 and 1. However, higher mutual information values means the feature provides more information about the target. Let's take a look here. Yeah, what we see is that mutual information between high correlated target and target is 0.5, which is good. And apart from this one, all the rest pretty small. And we're moving to the weight of evidence. So weight of evidence is a way to categorize or to bin, apply binning to your feature and to estimate how informative it is, or how it describes the target. Positive weight of evidence indicates that the category is associated with higher likelihood of the target event. Negative is the opposite. and 0 means it doesn't provide any information. And on top of weight of evidence, you can calculate information value or IV. Judging by the information value, you can have some estimations on whether this feature or predictor is useful or not. Let us calculate for our dataset, and we'll take a look at the education. So weight of evidence for education. Basically, the whole analysis shows that information value is 0.73. So let's take a look into interpretation. It says it's very strong. Maybe it's overfitting or data leakage. Let us talk about analysis of variance or ANOVA, and that's a statistical test that measures the difference between two groups. How it can help us is we can estimate the importance of the feature in the data set. So we're not estimating like now the importance of the feature for the model, for any model. We're estimating how important the feature is for the data set. And here we can take a look, like sorted features by ANOVA statistics, and all our synthetic data. And we can see that top features are our features that we generated. That is interesting and it is expected. How to interpret ANOVA. It provides F statistic, and F statistic indicates that there is a significant difference in the mean values of the features across the groups, implying that the feature may have predictive power in determining the target variable. So basically, if we split the target into two values, and we can do so for binary target, it shows whether there is a difference in distributions for each subset. Let's review the chi-square test. That's a statistical test. It measures the statistical significance of association between each categorical feature and the target variable. The higher it is, the stronger the association or the relation between the feature and the target. We do have categorical values in our data set. And let us take a look. Here, surprisingly, we have our work class high dependent, not on the first place, but close to the work class. How to interpret it? The higher the score is, the stronger the association between the feature and the target. Actually, the same happens if we use select k best from the scikit-learn with the score function chi-square or chi2. Yeah, work class, education, marital status, relationship, sex. Relationship, marital status, sex, education, work class. The same. We're moving to wrapping methods, and the first one is the feature selection. We're moving to the wrapping methods, and the first one is forward selection. Basically, what it does, it starts with a simple feature and then appends another features from the set to take a look. What it does, it starts from the one feature and then appends more features from the feature set. And this one took 13 seconds, and this one takes something like 10 to 15 seconds. How you can use it? It's a sequential feature selector from scikit-learn feature selection. You provide the model, you provide the features, and direction is forward. And if you provide the direction backward, well, you'll have the backward feature elimination. And selected features, again, those that we've seen, backward elimination, It is same function, just different parameters. But the idea is for the backward, you start with the full feature set and eliminate one by one features from this set. Yeah, here you can have like the selected features by the backward selection. As for the recursive feature elimination, well, it tries to find the best subset together with exhaustive feature search. Just let's take a look. Normally it's pretty fast, and as I mentioned, it's super fast here, super fast and efficient. However, like the features happen to be synthetical here. But yeah, let's move on. Exhaustive feature search will try all the combinations of features to find the best one. It is super time and resource consuming. However, sometimes you can use it. I will use it just for the toy example for 252 subsets of features. It usually takes something like a minute here, but for the real data on the real data sets, that will be a huge amount of calculations. So normally, before you go to exhaustive feature search, you should eliminate somehow the features, at least redundant features, also or some features that you know that are useless. By the way, here we can have number of jobs showing the parallelization. Actually, CV3 here means that we have 3 cross validations manually do 3 times, and yeah, 53 seconds, and we have a selected features by exhaustive feature search. What about embedded methods? Well, we'll take a look at the most simplest one, and we start with the logistic regression. Actually, since this data set is classification, we'll discuss logistic regression during the next lectures. What you need to know now, that's an algorithm similar to linear regression, and it can solve classification tasks. Basically, there are several regularization techniques here, lasso and ridge, but let's run this thing and take a look. So money and education, drivers of success. Let's take a look at another feature set. This one will be from the L2 regularization, ridge. We'll discuss in details those regularizations, how they work and what's the big deal. But here the situation is similar, not the same, but similar. We also have the decision tree. So decision tree is basically an algorithm that allows you to have this if-else structure, tree structure, and basically you can get the importance of each node in this tree. And here relationship matters according to the decision tree, but also education and capital gain. You can get this feature importance from the decision tree classifier, and you can get importance from the coefficients of the regression. We'll discuss those details later on. And that is it for this part. Feature generation is where creativity and domain knowledge come together. By transforming existing features or creating interaction terms like dividing income by age to get an idea of income per life stage, and using domain specific knowledge to generate these features can greatly enhance our model's performance. For instance, generating debt to income ratio from debt and income fields is a common feature in credit scoring. From simple transformation like applying mathematical functions to them to creating interactions to time-based features where we can generate lag features or features indicating the duration, something like days since last purchase. We can also aggregate features in various ways and calculate statistics, and of course binding and categorization. And here where the statistics and transformation techniques are super useful. Feature generation is all about creating new features that help our models perform better by finding hidden patterns or combining existing features in useful ways. The benefits are clear. It can improve models' performance and reduce complexity by transforming data in a smart manner. However, there are challenges too. Generating many features can lead to overfitting, and working with a lot of data can be computationally expensive. In this coding session, we will explore practical ways to generate features and look at the impact they have on model performance. And let's get started. Hi, we will briefly discuss the feature generation part here. Feature generation is a huge domain. It contains of various ways how you can create new features based on the existing ones, based on the domain based on existing ones, based on domain knowledge, based on some aggregation, some advanced techniques like binning, categorization. You can also transform target and so on, but we'll briefly go through the most popular approaches. Let us import what we need to. We're operating with the house prices dataset. Let's have a short description. Let us begin transforming the features. The first transformation is one of the most common. Let us apply logarithm to skewed distribution, to skewed feature. This is this is the way we can handle the skewness. This is the way we can make the distribution less skewed. Yeah, basically it looks like this from left to the right. Although not all mathematical transformations are good. Imagine if we have a power of 2, well, it actually the power of 2 of the squared area will make everything even worse. What about the interaction features? This normally requires domain knowledge make because if you automatically make all the possible interactions between features, you could do so. There are approaches to do so, but normally that would be garbage in and garbage out. But if you have some domain knowledge, you could try. So here we calculate the ratio of the lot area that is covered by the building, represented by the ground, like above ground living area. This feature helps understand the intensity of land use. Basically, an interesting combination. And as for the userless example, we can multiply lot area to the year built. Actually, that makes no sense even from the graphical perspective. As for the domain-specific knowledge, so again, we can calculate price per lot area. That totally makes sense to have this estimation. However, you should be really precise if you use this type of feature in the data set. That might give you some data leakage if you encode in the wrong way. And let us take a look. So if if we divide sale price by the month, we'll have nothing interesting. The same goes with the time-based feature. We have a lot of interesting time representations. For instance, we can have the age of the house, the number of years since the house was built until it was sold. A pretty interesting feature, actually, I would say. There are some patterns here, and I would love to investigate this. As for the aggregation features, well, let's take a look. We can group by neighbor, calculate mean, or something else. And it's a valid point. It's an average lot frontage by neighbor versus sale price. And we can see patterns here. That is useful. What about binning? Yeah, we can bin the area, for instance, into categories for easy interpretation, like small, medium, so on. Very small, large, very large. However, If we do not know anything about the domain, just binning feature will bring you nowhere. It's like binning the price. Well, maybe it makes sense, but the medium here is super big, and from the statistics, the mean here is super big. I don't know if it makes sense to use it. And we're moving to the categorical features. You can use one-hot encoding, pair option. You just get a lot of binary features from the original one. And the label encoding again, frequency encoding. What frequency encoding does is that provide you with a frequency of this category in the whole data set. And yeah, we can combine categories. So it's something like house style and overall quality frequency versus sale price. Again, there are some patterns here and I would really love to investigate them. Let us take a look at the correlation of the features that we introduced. We can see here that some of them are highly correlated, and I would recommend getting rid of them. And there is an even negative correlation between sale price and house age, but this is a fair feature. You can also see here that some of the features are dependent on each other. Let's take a look at the correlation between old and new ones. Yeah, we can see here that the house age and the year built, they are negatively correlated. That's the super, since that's what we really did. Price per lot area is, again, lot area highly correlated, but in a negative way. That is understandable. You can, by inspecting these matrices, you can have a sanity check or kind of sanity check to know that the data processing you're doing makes sense and going in the right direction. And let us compare the models. So just to understand the impact of newly generated features, we'll compare two models, decision tree and linear regression, using the original feature and then both original and new features. The reason we're doing so is just to check how the model performs given the new features. Let's take a look. So here we just created train and test set. We splitted the data, and here is our, and that's our main part. So what we do here, we train decision tree regressor, then predict a portion of the data and evaluate the metrics. The same goes for regression, actually. So it's pretty straightforward, I would say. So no parameter tuning, nothing. Let us run this cell. We can estimate those models by the metrics. We can see here that the new features contribute for both decision tree and linear regression, since the errors dropped, and for the decision tree the error dropped 2 times, the MAP error. So it's pretty interesting result, showing that you can generate features and those features can be meaningful and useful. And together with the feature selection, you can have feature generation and feature selection. It's a super effective way to come up with the new features and improve the performance of your model. Let's just plot the feature importance and also the original sale price distribution, log transform sale price distribution. Take a look here. Define features. Yep. Here we are comparing the effect of the target transformation. What you need to be really careful is that if you transformed the target, like here, you will need to transform the prediction or transform the results. It highly depends on your pipeline, but keep in mind that you cannot use transformed target and the and the output of the model that was trained on transformed target for predicting the actual target. And let us compare metrics before and after. As we can see here, models with new features show better results. Let us take a look here. Yeah, target transformation also have the features remain similar to the previous ones. We won't stop here, but we will definitely have this topic when talking about regression. As for the coefficients, you can see that the biggest coefficients are here. The other is pretty small. It's interesting. Yes, but this one is like new features combined. Coefficients are original features. Let's take a look. That is it. Thank you. Let us continue. And this is the section on dimensionality reduction. Dimensionality reduction helps us mitigate the curse of dimensionality. As we add features, models become more prone to overfitting, capturing noise instead of meaningful patterns. Reducing dimensions helps with both model performance and visualization, making high-dimensional data more manageable. Feature selection also can be considered as a dimensionality reduction technique. However, we'll be focusing on feature extraction approach. We'll apply transformations to features to reduce the dimensionality to get into the lower dimensional space. So key techniques in dimensionality reduction. We have principal component analysis, or PCA, which is linear method projecting data onto fewer dimensions while retaining variance. And there is t-SNE. It's a nonlinear method for capturing complex relationships. It's great for visualizing clusters. UMAP is another nonlinear method similar to t-SNE, but it's computationally more efficient, preserving both local and global structures. It's often better suited for embeddings of high-dimensional data. PCA is a linear method. It finds the directions in the data, called principal components, where the data has the most variance. PCA finds the directions in the data, called principal components, where the data has the most variance. It then projects the data onto these components, which reduces the number of dimensions, while still keeping as much important information as possible. The concept of eigenvalues and eigenvectors is central to PCA. The eigenvectors of the covariance matrix represent the principal components. These are the directions among which our data has the highest variance. The eigenvalues, on the other hand, tell us how much variance exists in the data along each of the eigenvectors. In other words, the eigenvalues indicate the importance or weight of each principal component. This technique helps in creating new features that are uncorrelated and are linear combinations of the original features, simplifying our data without losing the significant insights. You can see the formula here for calculating covariance matrix, which helps identify the principal components. The data is then projected onto these components using matrix multiplications. This allows us to simplify the dataset, making it easier for models to learn without dealing with unnecessary complexity. For PCA, think of it as rotating your data to align with axes that explain the most variance. Each principal component is a linear combination of your features, uncorrelated and more compact. The red arrow, PCA1, indicates the direction of maximum variance, which explains about 56% of the variance in the data. Another arrow, blue arrow PC2, represents the next direction of maximum variance, explaining 26% of the variance. These principal components helps to identify the most informative directions for reducing complexity. And now let's focus on the right plot. The 2D plot shows the lower dimensional representation of the data after applying PCA. The points are now projected onto the plane defined by PC1 and PC2. The red dashed line, or the vertical one, indicates the first principal component, PC1, while the blue dashed line, or the horizontal one, shows the second principal component, PC2. These axes capture the most essential patterns in the dataset, helping to simplify the models without losing significant information. The visualization effectively demonstrates the transformation of high-dimensional data into a simpler form while retaining the key relationship and variance, suitable for both explanation and visualization purposes. t-SNE, unlike PCA, is nonlinear. It can capture interesting relationships in the data like those pockets, clusters that PCA might miss. It is particularly useful when visualizing high-dimensional data sets, for example, MNIST dataset like here, and it emphasizes local structure over global structure. That's why it's so good at finding clusters or visualizing clusters. UMAP is a nonlinear dimensionality reduction technique, which means it does not just rely on straight lines like PCA. It can capture more complex relationships. One of the great strengths is that it preserves both local and global structures of the data, meaning it retains the small details while also maintaining the overall shape of the dataset. And UMAP is commonly used for data visualization, projecting high-dimensional data into 2D or 3D to make it easier to understand. It is also very popular for clustering and embeddings, especially for data like text and images where relationships are complex. Compared to t-SNE, UMAP is faster and scales better for larger datasets, which is why it has become like a preferred method for visualizing datasets like MNIST. This one is MNIST dataset. In the example on this slide, each cluster of points represents a different group of patterns in the data. This shows how UMAP can effectively differentiate between different parts of the complex data, making it useful for both exploration and interpretation. This slide compares PCA, t-SNE, and UMAP, each offering unique advantages for dimensionality reduction. PCA is linear and computationally efficient technique, great for reducing dimensionality in large linear datasets, although it captures simple linear relationships only. t-SNE excels at visualizing clusters and local structures in the data, and it is suitable for smaller datasets due to its computational cost and hyperparameter sensitivity. UMAP combines best of both, capturing local and global structures and being more scalable. It's ideal for large datasets where both detailed and broader patterns matter. In this demo, we'll apply dimensionality reduction techniques on a real dataset. Hello, and let's take a look at dimensionality reduction approaches. We'll have an overview of three methods: PCA, t-SNE, and UMAP. Each of them is good for its own conditions. It has pros and cons and limitations, of course. Again, as always, we start with import, loading the dataset. However, now we use The user behavior dataset, what it shows, this dataset contains the description of the user behavior, like the amount of hours spent a day, or the operating system, app usage time, and on-screen time, hours per day, gender, age, data usage. We need to predict the behavior class. It's a multi-class classification task, but we'll focus only on the dimensionality reduction. We will use those class labels as the verification just to know if those algorithms really segregated the features in a way that they should be. We have description of fields, and our target is user behavior class. Let's have it. Let's scale. Since PCA requires scaling to use, that's basically it. To get PCA, you can use scikit-learn decomposing. To get PCA, you need scikit-learn. That's it. Let's take a look at the PCA. What happens here is we provide 0.9 as number of components, and meaning that we would like to have 90% of variance, and we want to have the number of components identified automatically. Then we fit transform the data, and that's basically it. So the rest is just nice scatter plot. This scatter plot shows the projection of our dataset on the two principal components, and the color here is the label, and the whole situation shows us that it's almost perfect separation. But let's take a look at the variance. Yeah, basically two components are more than enough to decompose the whole thing. So it's like 97% of the variance described by two components. And let us move to t-SNE. It's t-distributed stochastic neighbor embedding. Simplifying this is this tool tries to keep the close relationships between objects, but at the same time it tries to form clusters of the data. It takes some time to process, 7 seconds, and again, this approach shows us clear separation, which is good. However, this dataset seems to be linearly separated since PCA can separate this. The advantage of using t-SNE is that it is nonlinear. It can capture nonlinear dependencies, unlike PCA. PCA is linear. We're moving to UMAP. It's uniform manifold approximation and projection. UMAP requires separate lib, so please install it. It's UMAP learn. And basically the syntax is similar to the one we have for t-SNE. Number of components, random state, number of neighbors, and that's it. There are a lot of parameters, but we won't stop for the parameters. The idea of today's session is to show you that those methods exist and you can use them. Okay, we need to install it. Just wait a second. Okay, it took 13 seconds. Let's take a look at what happened. So this is separation of the clusters. As I mentioned during the lecture, UMAP tries to preserve the cluster structure and the global structure. And since this dataset is clearly separatable, that is what UMAP shows. The global structure is separatable and the clusters are separatable. That is it for the dimensionality reduction. Hi and welcome back. We are moving to the data splitting and cross-validation techniques. Splitting the data into training, validation, and test sets is a crucial step to ensure model's performance. We typically split the data with 80% for training, 10 to 15 for validation, and the remaining 5 to 10 for testing. The training set is used to feed the models. The validation set helps fine-tune hyperparameters, and the test set provides an unbiased evaluation of the model performance on unseen data. This approach ensures that the model generalizes well beyond the training data, avoiding overfitting. Imagine we're training the model to predict some function, and we're testing this model on the same data. And this is a methodological mistake. A model would just repeat the labels of the samples that it has just seen. This model would have a perfect score, but at the same time it would fail to predict anything useful on yet unseen data. And this is overfitting. To avoid it, it's a common practice to hold out part of the available data set as test set. And this is a flowchart of typical cross-validation workflow in model training. The best parameters can be determined by grid search technique. And here we split the data and we use test for testing, train for training and cross-validation, and a portion of data for the final evaluation. There are several different techniques for splitting data. The random split is straightforward, but it may not work well with imbalanced data. For such cases, the stratified split is useful as it ensures the class proportions are maintained in each subset. For time series data, we use a time-based split to maintain the chronological order, and there are also hierarchical splits, and they're useful for data that have a hierarchical structure, such as user or device data. And the cluster split ensures that the clusters of the data are not mixed between training and testing. So how random split works? The dataset is split randomly into training, validation, and test set, just using random function. It is best for balancing datasets where the distribution of classes or labels is uniform. The risk here is on imbalanced datasets. Random splitting may result in an uneven distribution of classes, leading to biased results. As for the stratified split, it ensures that each subset, training, validation, and test, maintains the same class distribution as the original dataset. It is best for imbalanced data or classification problems where it is important that the class distribution remains the same across splits. Example here is use stratified splits when working with a fraud detection dataset. There can be 1 or 2% of transactions that are fraudulent. If you apply random splitting, you might end up without any fraud in training data or in test data. Time-based splits are, well, as I mentioned, data split is based on time variable. Typically, the earlier data is used for training, while more recent data is used for validation and testing. And it is best for time series data where the goal is to forecast the future outcomes. The method prevents future data from being used to predict past outcomes, which would be unrealistic. You cannot predict past based on the future because you don't know the future. And example here is predicting stock prices or energy demand is based on historical data. Hierarchical split. The split is done in a way that respects the hierarchy within the data, splitting by users, devices, or locations. It is best for data sets with hierarchical structures where samples may be correlated within groups. And as an example here, in recommendation systems, splitting by user groups ensures that users seen during training do not appear in the validation or test sets, mimicking real-world scenarios better. And as for the cluster split, if data is grouped into clusters, and then entire clusters are used for training, validation, and testing, it is best for when observations within clusters are similar, but clusters differ significantly, ensures generalization across clusters. For instance, when analyzing data with different geographic regions, ensuring that training and test data comes from different regions. Of course, sometimes you need to have the same regions and train and test data, but we'll discuss this later. Cluster split. Data is grouped into clusters, and then entire clusters are used for training, validation, and testing. It is best for when observations within clusters are similar, but clusters differ significantly. It ensures generalization across clusters. Uh, when dealing with imbalanced data, we must take special care during splitting. And techniques like oversampling the minority class or undersampling the majority class can help balance the dataset. Stratified splitting is another way to ensure that class proportions remain consistent across training, validation, and test sets. Additionally, synthetic techniques like SMODE can generate new data points for the minority class to help the model learn more effectively. But you should take into consideration that sometimes you will spoil the data if you introduce synthetically generated one. So you should carefully use those techniques. So cross-validation is a robust way to evaluate model performance. In k-fold, in k-fold cross-validation, the data is divided into k subsets, and the model is trained k times. And leave one out, cross-validation is an extreme case of k-fold where each data point serves as its own validation set. It is useful when you want to make the most of limited data, but it can be computationally expensive. Just imagine going through the train process as much as the number of data points you have. The whole discussion leads to a key concept in machine learning, and that's a bias variance trade off. Bias refers to errors introduced by overly simplistic models. They do not capture the complexity of the data, leading to underfitting. Variance leads to errors caused by models that are too complex, capturing noise from the data and leading to overfitting. Our goal is to find a balance between these two to minimize overall error and improve generalization. When a model has high bias, it is too simple, it underfits the data, meaning it has high training and testing errors. In contrast, a model with high variance is overly complex. It overfits the training data, leading to low training error but high test error. Both cases lead to poor generalization. Let us have an example for MSE. Can be decomposed into three components: biased squared, variance, and irreducible error. Biased squared is the difference between true function and the average predicted function. Variance represents error from overfitting. Variance of the model, how predictions vary due to changes in the training set. And the irreducible error is the noise inherited in the data that cannot be reduced. And balancing bias and variance helps reduce the overall mean squared error. You can take a look at the equations and you can also calculate them on your own, but here is like the step-by-step calculation that decomposes the whole MSE from the definition to the final setup. To balance bias and variance in machine learning, we can reduce variance through dimensionality reduction, feature selection, large training sets, or regularization. Adding more features reduces bias but increases variance. Different models, such as decision trees, can be adjusted by tuning parameters like pruning depth. Ensemble methods like boosting and bagging offer powerful ways to manage this trade-off. And finally, cross-validation helps us fine-tune models for optimal performance by balancing bias and variance. Let us have some coding on data splitting topic.
Hello and welcome to the data splitting and cross-validation practical part. We will cover briefly different splitting techniques and cross-validation like key fold, stratified key fold and leave one out cross-validation. We will also briefly touch the smooth techniques. The smooth technique is useful when when you have to deal with imbalanced data, and we'll also gently touch bias variance trade-off. Let us begin. We started as usual. We mount the Google Drive. For this session, we'll need a lot of data sets. Here I have Iris dataset, I have Diamonds dataset, I have air quality dataset. I even have the diabetes data. I think it's Iris again and Diamonds again. Let's talk about random splitting. What happens when we randomly split? If there is no temporal information in the data or no hierarchical information or no clusteral information in the data, that is super useful. We can do so. We can just use the random splitting and that's what we get. So if the data is consistent, each part of the data will be present in training and test data set. That's the ideal case. However, I would like to warn you just to always have fixed seed. Like here, I prefer seed 42. You can choose whatever you like, because take a look here. Like the accuracy is 97%. Here, I am not fixing. I'm not providing any seed. And here accuracy is 90. Let's take one more. 97, 3, 90. Please always fix this. As for the stratified split, let's talk a little bit about stratified splitting. For this, we'll need the credit card fraud data. Have this data set. And this one is imbalanced data, meaning that the proportion of zeros and ones for target is like this. So it's less than 10% of ones and the rest is like normal data zeros. For this type of data, I highly recommend using stratified split. So what stratified split does, it tries to preserve the proportion of the data for each split, for train split, for test split, and for validation split if you split 3 times. Yeah, and this is the situation when you have a stratified split. I calculated the accuracy, the precision recall, and F1 score here for the simplest model, just to illustrate the situation. So, like, the model is super simple here, like everything from the box. Now, imagine that we do not use stratification for splitting. And even here, we can see that the numbers dropped, and they dropped only because we didn't use cross-validation. We just use cross-validation. Let us take a look at another example. Here is the bankruptcy, and the disproportion here is even worse. It's 3% for the whole data set. Again, let us repeat the same thing here. We will just have this stratified split data. Why we have so good accuracy here? Well, it's obvious. If we predict everything as 0, 96% of our guesses will be right. That's why accuracy here is not informative. Precision, recall, and F1 score are more informative. And you can see the metrics dropped just because we didn't use the stratified split. And the disproportion here is not the same as it was in the original one. So it jumps up and down. As for the stratified, the proportion is fixed. Since we're talking about imbalanced data, let us take a look at SMODE. So I highly recommend paying some attention to imbalanced learn. It's a super nice lib that you can use for when dealing with imbalanced data. And as for this mode, basically you need to prepare the data for it. You should use mode on training set only. Then you should transform your data if you need to. And only then you just have this fitting, and this mode generates more data of the minority class synthetically. And here we can see that, well, we have some numbers. They are not great anyway, but those numbers will help us improve. SMODE can be used for balancing data, so we can apply it to the existing data set in order to make the disproportion not that drastic. Let's take a look. The initial distribution was like this, so it's like 9,900 to 1. So 0 means like the one class and 1 means another class. After applying SMODE and undersampling, we have not that, not, and after applying SMODE and undersampling, we have a better distribution. And again, use imbalanced learn, because I used SMODE from here. Over undersampling, highly recommend using it. And SMODE can be used for imbalanced classification, for oversampling. Here we try to find the best K for SMODE parameter. We can notice that, well, this one is better. So 5 neighbors might be a good pick. And this is the hyperparameter of the algorithm and of the pipeline. So you can use it, because here we use random undersampler, meaning that we reduce the majority class, SMODE for populating the minority class, and decision tree classifier to provide some calculate, and decision tree classifier to calculate something on one of the ends. Let me also mention that there are different approaches of cross-validation. So there is a k-fold stratified, k-fold and repeat stratified k-fold. You can use a lot of them. They are located in the model selection in sklearn. You just take a look at them and pick the one you prefer. There is great documentation here. So you don't need to write your own stratified splitter or something like this. It's already written in. And let's take a look at the time-based split. When it is helpful is you have data related to time, and you should take into account that you cannot randomly split the time series data. The time series data has a structure, it has relations, it has autocorrelation, and the whole data structure is against, and the whole data structure motivates you to use it as a sequence. Let's take a look here, and by applying, let's take a look here. So the easiest way is to use splitting, just to cut out the part that you need. It will be the history and this will be the future. But you should always take into consideration that let us imagine that we take time series data and we are just randomly split it. Let's see what happens. So nothing great. Like so mean square error here for random split is 0.43. Sometimes it's not the best choice to randomly select. However, for this particular case, the mean squared error is lower than when using like the chronological order. That is interesting. You can also use time series split. It is available in sklearn. So what it does, it provides you with the time series splits. You end up here and you can have the mean of all the approaches you had. Let's briefly talk about hierarchical split. So for hierarchical split, imagine that you have something like a school and you need to separate people from the same school from the train, test, and validation. So only people from a specific school can go to train, to validation, and to test. Sometimes that is useful to validate how your model works for different subsets or groups. And as I mentioned here, so we can separate by testing, training by school ID. So here, like school ID, won't be intersection. Here for school ID, there will be no intersections in train and test. Okay, hierarchical split. In this complex hierarchical split, we need to ensure that all data from the same school is either in the training or test set. This means that if we put a school in the training set, all classrooms and students from that school must also be in the training set. And this hierarchical approach avoids leakage of like school level characteristics between training and testing. Um, it can be easily done by the group shuffle split function, so you don't need to write it on your own or something like this. And we can see here, so the original data set, the training set contains only schools with ID 1 and 3, and testing set contains school only with 2 and 4. And as for the cross-validation, since we're several times mentioned the cross-validation, it's stratified k-fold or k-fold. You can use whatever you like, whatever you think that is useful for you. Let's just take a look at it. What it does. So we describe what it does. We describe the number of splits, whether we need shuffle or not, and random state. And here we have the features, we have the target. We also need to provide the scoring function. I provided several here. And CV results will be the list of data from the cross-validate function where you provide model, your data, your target, number of k-folds and all around it. Scoring functions and verbose means like whether you need information about the processing or not. And here we can also have this information and yeah, we have it and it's interesting. As for the leave one out cross-validation, that is similar to the key fold. However, Like you iterate over each element in the dataset. You can do so, that's an easy task, but for the huge dataset, it is not that applicable. And let's move to bias variance. So bias variance provide an interesting concept of how to treat overfitted and underfitted machine learning models and how to treat the errors, how to decompose the errors of machine learning models. Here we'll utilize the data from the existing data set of housing. So we just select features and targets here, split the data. Please use train test split. It's super nice, super useful. It has a lot of features. Yeah, linear regression with high bias, decision tree with high variance, since decision trees are normally overfitted, and random forest has a balance between two of them. That's a description actually. So this is the way we train the model. Yeah, and we'll plot the bias variance trade-off. We will plot predictions. I would say it's, for me, it's hard to judge by those mixtures, but we can take a look at the matrix, and according to matrix, the random forest is the best one, and that is obvious because random forest is an ensemble method, and it is super resistant to overfitting. And this is it. Thank you very much, and see you.
Hello, hello, and let us continue. And we'll be talking about data leakage. So that's a funny meme, and sometimes it's true. Data leakage, it is when information that wouldn't be available in practice finds its way into the training process, leading to overly optimistic performance. For example, in fraud detection, if we include features in the model that are only available after the transaction is complete, for instance, fraud labels or post transaction data, the model will artificially perform well in training but fail in real world scenarios. There are different types of data leakage, and train test communication happens when information from test set is used during training, leading to artificially high performance. Target leakage occurs when features that contain future information about target variable are used, which means the model has access to information it wouldn't have during real life predictions. For instance, including features like medication prescribed to predict whether a patient develops a certain disease can result in a model that performs unrealistically well since medications prescribed after diagnosis. Uh, Time series leakage happens when future data points are used to predict past events, such as including future stock prices in the training set for a prediction model. This results in inflated performance during training but fails in real scenarios. Data leakage can be very harmful. It gives you a false sense of model performance during training because the model has access to information it wouldn't normally have in a real world scenario. This results in overly optimistic performance metrics and models that perform poorly when exposed to new unseen data. Proper separation of training and testing data is crucial, and we must be mindful of how we engineer our features. For time series problems, always make sure that training data precedes validation and test data chronologically. Similarly, avoid including post-event data in training features, as that would be unrealistic during model deployment. Preventing leakage is not only about training and testing separation, but also about critically assessing which features reflect the present and do not imply future states. Let me show you some examples of data leakage.
Hello and welcome to the data leakage session. I will briefly talk you through the several data leakage types and we'll take a look at them, discuss them a little bit, and I'll show do and don'ts. Let us begin. And as usual, we start with importing everything and getting ready. So as for the first example, it's train test contamination or like the future information leaks through the normalization or standardization approach into the existing data, into the current data set. How it happens? Imagine you have a data set, you read it, then, well, you scale it because you see that something is wrong with the data, or maybe it requires scaling because you will need to pass it to the machine learning model that requires scaling. Then you split it and then you try to do something else. This could be actually an error, and this will be an error because here you scaled the whole data set. You applied scalar for the whole data set, not for the train part. With this, you won't have an adequate situation when parsing the test set because you have seen the data in the test set when when you created this scalar. The safest option is to feed the scalar on the train set and apply this scalar for the test. So yeah. The second type of leakage is the target leakage, the most common one. So just feature containing information about the target. Imagine like here you just forgot to exclude the price from the data. It happens more than you might think. So again, please take a look at the data and always monitor it and pay attention to it. But let us talk about time series leakage. So it's basically about using information from the future to construct features as of now. And if you do not use this data, if you just split randomly, uh, you could have this spoiled data or spoiled features and they won't reflect the actual data set. However, if we use like if we separate, yeah, we will use this information and we will have this information more accurate. So sometimes the leakage could come from derived features, again from improper feature engineering. For instance, if we calculate price per square feet, that's a great feature actually, but this involves sale price, and that's a leakage. You can calculate price per square feet, but you need to use more sophisticated estimations of the price, not the exact sale price. And yeah, as for example here, like ensure that derived features do not use target variable information. Let us move to data leakage from data imputation. And as I mentioned, for the scalar, for the imputer, it is the same. Please use only train dataset for imputing. Just like this, you can take a look at this approach and see it. So just to sum up, please pay attention to what you're doing. Please always validate the features, the targets, and the operations that you do. Ideal case is to have a pipeline. If you have pipeline, the pipeline will help you organize all the procedures in a way that you will be confident that they go one by one and they're described in one place. Thanks, everybody. See ya.
Welcome back. And now let's talk about data preparation pipelines. So, a data preparation pipeline automates the steps required to transform raw data into usable format for machine learning models. Pipelines handle data cleaning, feature engineering, scaling, ensuring consistency between training and testing sets, which prevents issues like leakage and improves general performance. By creating and using pipelines, we make our data preparation process efficient and reproducible. So the components of data preparation pipeline normally include several components. First, cleaning the data, then engineering features, whether by encoding categorical variables or creating new features from existing one. Also, scaling is involved, and dimensionality reduction sometimes to ensure that the same transformations are consistently applied to both training and testing data. Using pipelines provides a number of benefits. Pipelines ensure that your data transformations are applied consistently to both training and test sets, preventing data leakage. They also automate the process, which is especially helpful when dealing with large datasets. And overall, properly prepared data improves the performance and generalization ability of machine learning models. This is the example of pipeline. Basically, you can take a look on the flow, and we apply numerical transformer. We define numerical features, apply numerical transformations, then we define categorical features and define transformations for categorical feature. Then both of those transformers are combined into a bigger pipeline and a column transformer pipeline. And then in the end, we have the big pipeline of preprocessing, which involves like dealing with the data. And we apply classifier, so the data from this preprocessor goes into the classifier. We define the splitting. Here I use random split. And then I feed the pipeline to train data, meaning I apply all the transformations, and then I can have a prediction with the pipeline on the test data. That is basically it. So in total, it's 70 something rows. That's a whole pipeline of solving a machine learning problem. Let us let us have some coding. We will take a look at pipelines.
Hello and welcome. We are discussing pipelines. Basically, I'll just briefly show you the pipeline and the steps of the pipeline in this video. Your homework will be to create your own pipeline. We start as usual, the data. We have a lot of inputs here. Not all of them are necessary. That's a little bit of a mess. Okay, now I will show you what a pipeline is. Pipeline is a crucial part of the scikit-learn. So basically, a pipeline is a sequence of steps. You can design it on your own. And the main advantage is to have everything in one place, traceable, and you can always change the pipeline. And the operations are stored like in a single logic. Again, here we have simple feature engineering, features and targets, splitting. We do not need here stratified splitting since sale price does not require it. And now we define the preprocessing steps. So we need to have numerical features and categorical features, and we'll need to process them. And for each of them, we define a pipeline. So numerical pipeline will consist of those steps. We'll use imputer, then apply polynomial features, then apply scalar. Then, since we have these polynomial features, we'll need to apply PCA with some number of components. And then we'll select K best features and use it. As for the categorical, so yeah, we'll have imputer and one hot encoding. Then we can have this. Then we combine everything in the column transformer. Basically, it describes which operations to apply to which columns. And here we define that, well, we have numerical columns, and we would like the numerical transformer to be applied to numeric features and categorical transformer and categorical features. Also, you can describe how the metrics are calculated. That will be useful if you need to run several experiments. So yeah, here we define like the linear model as a pipeline of preprocessor that we defined earlier, and the linear regression. It's basically can be run here, and the same actually goes for the decision tree regressor. As for the linear regression, that's easy. So define pipeline as a linear model, then we predict with it, calculate all the metrics, and we have everything. And in the end, we can even save the whole pipeline as a pickle, and that's again super useful thing. Just use pipelines and save them, and you'll be happy to have them, since you have a pre-processing as a pipeline. You have the feature inside as a feature generation inside as a pipeline. It is super useful. And the same goes for the decision tree, actually. Then you can have this grid search CV, meaning that you would like to find the best parameters from this parameter grid with this cross-validation five folds, this scoring function, and this number of jobs. Yeah, basically your pipeline will be validated through this grid search approach. Yep, so we have the linear model coefficients and the decision tree model coefficients. And I believe we have a winner. The average percentage error is lower for the linear regression. Oh, yeah, that's a tricky one. MAPE is lower for the linear regression, but RMSE is higher for the linear regression. Yeah, that definitely requires further investigation. That is it. For 100 rows, we have a pipeline ready. So basically, we can save this thing, and we saved this thing as a pipeline, and we can reuse it just by getting it from the pickles. Thanks, everybody, and see ya.
Welcome back. So let's summarize what we've covered today, and we've covered a lot. So summary and key takeaways. Feature selection, it's key decision, use filter methods for quick, simple selections. Wrapper methods for higher accuracy at the cost of computation. And embedded methods as a balance between the two, especially when regularization is needed. Feature generation, here use domain-specific knowledge to create interactions or time-based features. Be mindful to overfitting when creating too many features. As for the dimensionality reduction, use PCA when linearity is assumed and computation speed is a crucial. For complex nonlinear relationships, you can use t-SNE or UMAP for better visualization and clustering. As for the data splitting and cross-validation, always use cross-validation to assess models' robustness. For imbalanced data, stratified splitting provides representative class distribution in each fold. As for the data leakage, prevent leakage by keeping training and test data strictly separated, and watch out for features that may leak future information into the model, especially in time series data. As for the pipelines, automate and bring the consistency in data preprocessing by building pipelines. This prevents human errors and data leakage during the transformation. Thank you for your attention. I hope you found today's session insightful and you are ready to take your data preparation skills to the next level. And remember, a solid foundation in data preparation sets you up for success in machine learning.